Professor Varadharajan gets his mic fixed. So let me introduce Professor Varadharajan. So as he's a faculty at RRI in Bangalore. So he has worked in quantum gravity, did his PhD from Syracuse University, and then postdoc at University, then joined in 1997 at RRI. So let's not wait anymore. We already are slightly delayed. And welcome Professor Varadharajan for his talk on quest for the quantum mechanics of space and time.
Okay, so thanks a lot. Thank you, and Ankur, for inviting me. And Ramadevi is not here, but for all the arrangements. So yeah, it's the first time I've come here. It's really nice, very, very nice to be here. Today I thought I'll tell you a little bit, try to share the excitement I have for my own field of interest, which is quantum gravity. So what is quantum gravity? Quantum gravity is an ongoing effort, as yet incomplete, to construct a quantum mechanical description of the dynamics of the gravitational field. So non-gravitational interactions like the strong and weak nuclear forces or electricity or magnetism, all of these have a satisfactory mechanical description. And in fact, this is the description which underlies the standard model of particle physics. So somehow gravity has eluded attempts to provide it with a quantum mechanical description. And the reason is that gravity is completely different from the other interactions. So what I'll do in this talk is try and tell you why it's so different, what are the conceptual issues which crop up, tries to construct a quantum theory of gravity. So that's where I'll get started, and then we'll go on with the talk. And if there is some obstruction in my train of explanation, then please interrupt me. If there is something which is peripheral to say, then we can discuss it in the question and answer session. All right. So, and it's a little bit of a mixed audience. So just feel free to stop me if there is something which you, if step one is, before step two is not understood, just stop me. All right. So here is the plan of the talk. Before I go to I'll say something about our classical theory of gravity, which is Einstein's theory of general relativity. And Einstein's theory has a conceptual framework which is very different from that of Newton's gravity, or for that matter, for any other interactions which are non-gravitational. And if nothing else you get from this talk, then what I want you to take away, classical gravity, unlike other interactions which unfold on a fixed space-time, classical gravity is actually a theory of space-time itself. Okay, so that is really the sort of big lesson which I would like to draw from this first part. Then we'll come to quantum gravity, and I'll try to estimate for you when quantum gravitational effects are likely to be significant. And we'll see that quantum gravity will be significant at unimaginably high energy scales, orders and orders of magnitude larger than the LHC. It's basically impossible that we are ever going to test quantum gravity through accelerated measurements. And given that that is the case, it's a completely legitimate question as to why one is doing this activity in the first place, if you're never going to be able to test it directly. And there are some reasons which I would like to share with you, which come from the mix of extremely exotic situations, like right in the beginning of our universe or deep inside black holes. And so I'll talk a little bit about that and try and set up why one is interested in quantum. And then I'll come back to the topic of possible contact, if at all it is possible or not. Then I'll give you a laundry list of approaches to quantum gravity. And finally, if there's time, I'll tell you a little bit about the approach, which is called loop quantum gravity. So let's start with classical gravity. And again, feel free to also speed me up, if, because I don't know where to pitch it, whether there are first years involved, etc., etc. So let's right. So classical gravity for most astro terrestrial purposes, Newton's theory is an absolutely accurate theory, and we can live with it. And in fact, that's what practicing astrophysicists do. But the correct theory is really Einstein's theory. And so if one wants to look at extreme gravitational fields, by which I mean, things, as I said, sort of side black holes or in other, in neutron stars, etc., very close to them. If you want to look at the gravitational fields there, then you really have to put in Einstein's theory. To look at very accurate descriptions of gravity, then you will find that Einstein's theory than Newton's theory. The conceptual structure of Einstein's theory is completely different from Newton's theory. So for example, if you have the sun and you have the earth moving around, I will just tell you that the sun exerts a gravitational force on the earth. So instead of the earth going straight, it curves its trajectory because it's pulled towards the sun. What Einstein will say is something different. He'll say that the sun distorts the space-time geometry around in its vicinity, and the earth tries to go as straight as possible of geometry, and so it appears to us as if it's going in a curved trajectory. Okay, so it's a completely different way of looking at things. And what is relevant if you want to write down a theory of space-time, then of course what you have to ask is, what is the mathematical object characterizes the geometry of space and time, because that is, after all, what is gravity. Okay, so gravity is the geometry of space-time. And it turns out that the mathematical object which characterizes this geometry is something it's the distance between a point and its nearby points. Give me the network of distances of a point and all its neighbors, then you have characterized the geometry. So let's do this in a couple of examples. First of three, to get my point across. First, spatial geometry, and let's go simple to 2 dimensions, right? The surface of this table, right? Now I can ask, what is the distance between 2 points with coordinates x, y, and a nearby point which has a coordinate x plus and y plus dy. And of course you just use Pythagoras' dl square is just dx square plus dy square. Okay, so that is just obvious, and that is what the geometry of the plane is like. But it turns out that you can do the converse. So I can give you a plane worth. So imagine that I have a plane's worth of points, but I don't have any idea between them, right? So there are some x and y coordinates of x and y. I give you a point, and then I arrange these points in such a way that the distance between a point located at xy and a point located at x plus dx and y plus dy given exactly by that. And if I ask you to do this, you will find that you will necessarily have to arrange these sets of points in a planar geometry. Okay, so the distance function is primary and the geometry is what is emergent. That is the point I'm trying to make. Similarly, you can do it for the sphere, right? So you can go to polar coordinates, and let's say we are looking at one sphere of fixed radius. Then the distance between 2 points which are located at angular coordinates theta and phi, and theta plus d theta, phi plus d phi, close, just given by this expression over here, as you know. But again, what you can do is, if you are given the topology of a sphere, and if you are given a set of points without any distance function between them, so again a sphere worth of points, and then you try to arrange them in such a way that the distance between 2 nearby points is exactly this, and you will get emergent from this a unique arrangement, which is the geometry of sphere. All right. So it is the distance between a point and its infinitesimally nearby points which completely determines the geometry. So this was about space, right? So now let's go to space-time. And as we saw, you can get a curved geometry like the geometry of the sphere, or you can get a flat geometry like the geometry of the. These options are there, right? So let's now go to the geometry. And here there is a little bit of an extra thing which happens, which is very profound and which changes things, which is that let's go to special relativity. Special relativity, it turns out that the distance between points which have inertia x, y, z and t, and a nearby point which is x plus dx, y plus dy, z plus dz and t plus dt is this object dl square, where this is exactly like in space, like in three-dimensional space, but then you have a negative term over here. In other words, once you go to special relativity and you try to, these distances can be negative, they can be positive, and they can even be zero without the points being at zero separation because of this minus sign. So the negative are all time-like, the ones which are zero are like, and the ones which are positive are space-like. And I'll sort of a diagrammatic description of this geometry. And then if you, again, somebody tells you that I give you a 4-dimension worth of points, x, y, z and t, and try and arrange them so that the distance function between this, then you will find in a precise sense, in a precise technical sense, of this arrangement will be zero. Okay. So this arrangement of points gives you an emergent geometry which is flat. It is not curved. So I'm just repeating this in diagrammatic, right? So let's, I can't draw in 4 dimensions, so I'm just suppressing the z coordinate, x and y, and you can, let's, perch on this point with its x, y and t, okay? And actually this should be ct, I missed a factor of c, but let's perch over here, and then you can see that these guys, this is exactly where the distance over here is equal to c times t over here, right? It's at 45 degrees. All right. So this is the trajectory of light. Okay. If I go inside this and I look at points over here or over here, then you will see that the distance is less than what light would have taken for the same time. So all the points inside are connected to this vertex by things reach with velocities less than that of light, right? Does that make sense? These points over here are along light rays, all the points inside where the temporal part dominates over the spatial part, so the distance is negative. These guys are points which can be reached by this fellow emitting, which are physical signals which travel less than the velocity of light, at most the velocity of light, which would be the surface. So this is called the light. This is a very important concept for what I want to say for the rest of the talk, right? It will come up repeatedly. Similarly, so this is the future light cone. If I choose signals to the future, then I can cover all these points inside this huge light cone over here, which goes well. Similarly, if I'm looking at this guy, this person over here can signals from within his or her past light cone. So all the things which can be cause something over here are over here, and all the things for which this can be a cause are located over here. If you have something over here where the spatial part is dominating over the temporal part, then this will have to have a speed. Anything which you try to send over here would have to have a speed greater than that of light, which is physically impossible in special relativity. So you can, this simple geometry over here not only tells you, not only that the space-time is flat, but it also tells you which events can cause what the causal relations are between points in space-time. What can you be influenced by? So the geometry really is very, very powerful, right? Because it tells you about the causality of that system. Any question? Okay. Okay. I mean, feel free to ask, because if you ask, then I know that you're not dead, right? That you're still, and something is, I'm talking to people who are alive, right? So you can always feel free to interrupt. Okay, so now let's do, sorry. Let's now go to general relativity, right? So this was the space-time of special relativity, which was completely flat. Relativity, just like in the case of the sphere, where you had a curved spatial geometry, general relativity, you do admit curved geometries, right? In fact, it was a curved geometry for which the Earth went and seemed to be traveling in a curved path. So the network of distances, you give me this 4-dimensional worth of points, and I give you a metric, which is this distance function. Again, this network of distance specify, and you can see the emergent geometry, which in a specific technical sense, you can compute its curvature, and it turns out to be curved generically, okay, depending on what your input. Once again, nearby points can have distance, positive distance, or zero distance. And once again, negative distance or zero distance, they can be connected. So they are causally related. The ones which have positive distance, where the spatial dominates over the temporal part, you cannot ever communicate with them. So this is a local statement. You go to a point, you look around it, and you have still a small little light cone over there. And it's very important, signals are always within the light cone. Okay, that is the sort of key concept which I wanted to transfer. Now, you might say that, well, this is all perhaps a lot of science fiction, and maybe, it's difficult to really see that this is all. And of course, around 15 years ago or so, I would not be able to give you a concrete example. But now you have this wonderful example, which is ubiquitous and which you use all the time in your daily life, which is the GPS. So what does this have to do with curved space-time? Well, it turns out, so how does this GPS work? In a very simplified way, your cell phone is a receiver. It receives signals from a minimum of 4 satellites which are orbiting. So you have 4 streams of data, right? So when the satellite sends you a data and you're receiving it, it tells you, it gives you, it's time stamped. Okay, so you know the location from where it's coming, time at which it has been sent. And then you have 4 unknowns, right? Which 3 coordinates and your time coordinate. That's the simplest way of thinking about it. So you have 4 unknowns, you have 4 streams of data, and by knowing the trajectories and how long the data, they all intersect at your point, you can invert the relationship and you can find x, y, z, and t. Okay, so that is basically how you tell your position using the GPS. But clearly, it is extremely important for all this, because every time in which it was sent from there, the time at which it arrives over here is what you want to find out. But because the satellites are away from Earth, right, the gravitational field is lower than on Earth, or if you're talking Einsteinian, then the curvature of the Earth of space-time is more than that at the satellite. And therefore, the geometry of space and time is different near the satellite and different near the Earth. And therefore, clocks in the satellite will tick differently from the clocks on Earth. All right? And if you account for that difference in the timing of clocks due to the curvature of the gravitational of space and time, you would find that your GPS would stop working. If they were, your GPS would stop working in around half an hour. For military, probably in a few minutes because they have a much more accurate code. So it is true that it is not some mechanism of the clock which is, going bad, or it is the flow of time itself is different far away from Earth and on Earth. Okay. So I mean, I hope to have convinced you that this is not just science fiction, this is actually real, right? When I am close to you, I distort the space-time around you. Very, very low, all right? And therefore, not only your rods, the way you measure length changes, the way you measure time changes as well. And this is simply true. So it's as astonishing a concept as probably as quantum mechanics, at least to me. Right? Completely different. You never, I mean, it just sounds so weird, but it is true. Okay, so now taking your silence for consent that you agree with the idea and that it's all good, let us do a thought experiment, okay? Switch off the gravitational field, all right? I have the flat space-time or special relativity, which I showed earlier. What happens is that the dynamics of, all matter, light, everything just unfolds on this fixed space-time, all right? Nothing, conceptually, it's all good, right? Whether you're doing physics you're doing, right? All your experiments, all the quantum equations, everything unfold on this fixed space-time. And we are good. Now I switch on classical gravity because there's matter all around, and so the space-time is curved, and your grid of spatio-temporal distances, they slightly change so that now space-time. But conceptually nothing really changes because it's a fixed space-time, and all your quantum fluctuations, all your classical thing, whatever you have to do is unfolding on this fixed stage. Nothing conceptually has changed, all right? Good. Let me switch on quantum gravity, by which I mean quantum fluctuations of the geometry. So when you have quantum fluctuations of geometry, I really want you to think about what that means, what that could possibly mean, right? So the only thing it could possibly mean is that this grid of spatio-temporal distances, which are fixed, are quantum fluctuations. Okay. So what was just a fixed stage, which was space-time, where everything happened, has now started fluctuating. So this stage, which was an inert stage, has now come and has joined the rest of the actors as well. And when that happens, the light cones, which were strict light cones, right? You knew exactly I could cause, I could shoot a bullet and someone over there would, probably get injured, or something bad would happen, right? So, but now everything is fuzzy, right? Even light beams, you're not really sure where they go because the geometry of itself is now subject to quantum fluctuations. So the notion of causality, whether one is to, I cannot say 100% whether something is to the future of me or not, right? So everything now starts becoming fuzzy. Classical space-time loses its meaning, and what we really want to construct is a quantum mechanics of space-time itself rather than a quantum mechanics in space-time. And this is really the principal conceptual difficulty in quantum gravity. So by now you should be having some kind of like out of body experiences or something, because this is just totally weird, right? I mean, if the gravitational field is actually quantum mechanical at some deep level, then these are questions which you have. And this is why it is so different from other interactions, and that's why it's so difficult to construct a theory of quantum gravity. Yes.
What do you mean by that you keep both space and time in what operators?
Absolutely. Right? There are now operators. What is the dynamical variable? The dynamical variable for my theory is this distance function, right? So now the metric is going to fluctuate. It's going to be subject to quantum uncertainties. Yes. No, so let's take an example of something else, right, which you're familiar with, which is or any other. Ultimately, so that's the whole point, right? The language of nature seems to be quantum mechanics. So in principle, it is intrinsic, right, to any dynamical entity subject to quantum fluctuations. So it is not that it is caused by something or not caused by something. In our very description of nature, we believe that at base the right thing is quantum mechanics, and there may be limits where the classical approximation is a good approximation, which is where live in this classical domain, right? But the belief is still that the underlying true language of nature is quantum mechanics. So it is not that something is causing something or the other. It just is. That is the way nature is, right? Like in particle quantum mechanics, right? You don't say quantum, it's like that. It is just the way it is. It's a new discourse, it's a new window. So you take that window and you put it onto space-time, and then you completely, it's all lunacy, right? Because you just don't know what. So there's a lot of confusion. No, not at all, right? I mean, there can be intrinsic, and in fact, the gravitational field has its own degrees of freedom. Gravitational waves, for example, right? So, of course, if you wanted to say that there is no mass at all ever, energy ever in the universe, then nothing can be, there is no source of curvature. But that is not a statement, right? So basically, it's like saying there is no charge or there is no electromagnetic field, But given the fact that you have a dynamics, right, and you are fitting that dynamics in a theory, you can also look at sourceless solutions where you don't have matter present, and there will be intrinsic fluctuations of the geometry. Okay, at the very now, when will be important? That is certainly, and why is it that we are living very and when you say that the talk is 5:30, then maybe, but you know that it started at 5:35, right? There is no fluctuation over there. You're happy, no? So why is that happening? If I'm telling you everything is fluctuating. So it's also true that if you look at, for example, very, very small objects in the lab, or you look at the Bohr atom, etc., then there you will see quantum fluctuations, right? So there, the whole business of how large objects, then quantum fluctuations are not important, etc. This is a deep, I think, ongoing topic. We really don't understand everything about it yet. But what one can do is one can say, okay, you tell me, can you estimate when quantum gravitational fluctuations are really going to be important? Okay, so that I can do for you, and that's what we'll do on the next slide. Okay. Very good questions. I want you to engage with this and really feel completely confused, because that is the status of anyone who's in this field. You just don't know what's going on. Yeah.
How do you put the equations in the metric tensor?
Good question. So people do it in lots of ways. I will tell you towards the end of the talk what I do. Fair enough? Yeah.
How is this not a problem for non-gravitational fields?
Sorry, how is
this not a problem for non-gravitational fields? It's a quality that helps to know the quantum electromagnetic field.
Right. So there you see, what happens is that you have to write down. So you have a Lagrangian. I mean, have you done Lagrangian? So you have an action. And in quantum mechanics, one easy way to see it is what is the, how is the is the action, how close is it to Planck's constant? If the action is very close, if the total action or whatever configuration you're seeing, what you're focusing on is of the order of Planck's constant, that is when fluctuations you're going to notice more. Okay, so that is like a thumb rule of when you will, and this is what I'm going to come to in the next. It's also a good question, and we can discuss it more later. That in conventional quantum systems, when is it that you fluctuations? When do you go to the classical limit, right? So for quantum mechanics, already you can just do the uncertainty principle, right? And there you will see when the masses are large, you will not have, will have very low uncertainties in the velocity simply because of mass function and because of the smallness of h bar. Okay. So again, depending on which interaction you're looking at, we can go and look in more detail.
Means you started the talk by saying that it's difficult to unify quantum theory with the gravity,
Yes.
but whereas the other, the electromagnetic,
Yes,
we were able to do this
that's
field
correct.
theory. So what is for not being able to do that with the gravity, but being able to do
Very good. So the reason, as I said, there is a conceptual reason, right? When you look at, say, electromagnetism, or I'm not saying it's easy. It's terribly difficult. One still doesn't understand QCD completely. But write down a Lagrangian, right? One can apply the rules of quantum theory, which are applicable in the context of a fixed space. You know what space and time is, right? You can write down your coordinates, no? You can take Fourier transform, go to Fourier space. You can write creation annihilation operators, or I don't know how much you've done. Basically, the fact that you are anchored on a fixed space-time allows you to do a lot of things, and conceptually also there's no problem, right? I have my space-time, things are going along, I know what time is. There's no conceptual problem of my measuring at what time, the particle went and hit some other particle. But now, because gravity has to do with space and time itself, I don't know what to do. For example, any of the other interactions, you know very well what is cause and what is effect, right? This is the speed of light, this is what it is, I don't know where my space-time coordinates are, everything is clear. I don't even know what causality is, right, at the very base, because my whole notion of space and time is fluctuating. So how do I formulate even what is causality, right? It's a fundamental notion to anything. What do I check for, right? So as you slowly think, it will slowly come to you that no, this is something which is very weird, and I really don't know what I'm doing, and I'm very glad. I mean, I think these are things which will slowly seep in. I don't really have to finish a whole set of material in this talk. What I want to get to you is this feeling that, what is going on, right? And that's nice that you're asking these questions. Okay, so let me continue. And let me just estimate in another way. I think there was a question about when quantum fluctuations would be important. Most naive and sort of easy way of thinking, perhaps when quantum gravity would be important. So when would it? What you can do is you can take the feature which are involved in gravity, which is Newton's constant, because general relativity is a relativistic, right? The speed of light, local speed of light is again the speed limit. So you have the speed of light, and then quantum mechanics where you have Planck's constant. These are full objects, and you can combine them in different ways, and you can get quantities which are of the dimension of length or energy or time, etc. Right? And these are called the Planck length, the Planck time, the Planck energy, etc. Just look at one of them, like the Planck length, 10 to the minus 35 meters. Okay, what, 10 to the minus 14? So, I mean, it's unimaginably small, right? Are you ever going to encounter those distance scales? I mean, forget about daily life, but in accelerators, no, you're not, because look at the accelerator energy. It's 10 to the 16 times the energy at the LHC. Okay, so as we are concerned, we don't know the mechanism as to how quantum gravity relax in our everyday domain and become classical, because we don't have a theory of quantum gravity. But we do know, or we can at least anticipate, that to achieve these high energies or look at these short distance scales, we would start having to worry about these totally weird things. All right? Is that somebody who asked me about quantum fluctuations? Is that okay? Does that make sense? Okay. Okay, so on the other hand, if I'm never going to be able to make a direct experiment, and I'm telling you, you can't, right? I mean, an experiment will tell me that it is just forget about it, right? So why care, right? I mean, why do we? There's some nobody. You're not going to be able to test directly, so why do you want to worry about it? And it's a legitimate question as to why one should worry about it. So let me give you some internal arguments which are from the point of view of theory itself. Fascinating arguments. So let me spend some time on a couple of them. Okay. So the first argument is what are called singularities, objects. So just like in Newton's theory, right? Newton's theory, you have mass distribution, then you can calculate the gravitational force or the gravitational potential. Here, you have a mass distribution or an energy distribution. So it's called the energy momentum, and that then will create curvature. And the energy momentum, and that is at least at the rough first way, right? So the Einstein equations, one side will give you a mathematical object which is called the curvature of space and time, and on the other side will give you the energy momentum tensor, and one will source the other. All right, so these are coupled equations. What is the solution of these equations? So suppose somebody comes and tells you about the solution of equations. Then a solution is just a single space-time geometry with some matter on it consistent. In other words, the matter curves the geometry, and on this curved geometry, that very much as it can. Right? So it's a coupled nonlinear system over there. Now, one looks at the space-time geometry of our universe at large scales, cosmological scales. So you go and you look out, then you find that the universe is the same in this direction and in that direction. It is homogeneous. Okay, so there is no very large scales, it is homogeneous. At small scales, of course, I can see Arunima here, I can see Ankur here, they look completely different, right? But if I go out large scales and I look at what happens over there, at those scales, everything looks the same. Okay? Now, when everything is the same, then there is no dependence on space, and therefore your partial equations which have derivatives with respect to space and time now have no derivatives with respect to space, and you can solve only ordinary differential equations. And you can say, okay, if I look at the universe and then I apply the Einstein equations, then I can integrate them backwards. And as I integrate them backwards, I find that the curvature in earlier rocks is growing and growing and growing. And then there comes a point at which this curvature just blows up. It becomes infinite, right? And that is the point which is the Big Bang, right? So the Big Bang is not a bang in space-time with our mantra from the first part, right? It is actually of space-time itself. That is when space-time started. Okay? Whenever you have equations in physics, just go bad because this is a case. You can't compute anything. The curvature is just going to blow up. So you have no idea what is going on, right? It just blows up and you stop. So then if you have faith in physical explanations, then you will say that you are pushing your theory beyond its domain of validity. That's the only way you'll get infinities in physics. Now, before curvatures become infinite, okay, the curvature has the units of 1 over length square. Before the curvatures become infinitely large, they are going to become 1 over to the minus 35 meter whole square, which is a huge curvature. It's called Planckian size curvature, but it will hit that. No? Before it goes to infinity, it will grow, and it will hit that. When it hits that level, you know that quantum gravitational effects are going to be important. And so, a very key question is, can quantum gravitational effects cure what was hitherto a singularity where things blew up, things became singular for the classical theory. So, in other words, classical general relativity is incomplete. In fact, very eager to give you give you guys another talk, but I think you're not to do with what are called the Penrose singularity theorems, and which has a lot of interesting history of the people involved. So if anyone is interested, then you can come and see me tomorrow and I can tell you all of it. But what Penrose showed and then what Hawking showed later is that these singularities are very generic. Only with this homogeneous case and everything coming, it's very generic. So general relativity is an incomplete theory. It predicts its own demise very often. And something has to come perhaps and rescue it, and the logical thing which will come and rescue it is quantum gravity. Therefore, that's a good reason to study quantum gravity, to have a better understanding of our universe in principle. Let me
Excuse
come
me,
to,
sir.
yes.
Sir, I quite understand
Yes.
that means you went to a current epoch, and
Yes.
that time you look at a homogeneous
Yes.
case.
Yes.
Then once you assume a homogeneous case, how can you go back using the same law to the
Very good. That's a very good question. So what this is sort of when and you write down what is called Big Bang cosmology, then it is very, very well validated by experiment. So if you go and you say it's basically at that point it's almost homogeneous and isotropic, and you evolve it forward, and then you put in a few bells and whistles, which I won't get into, maybe at the end of the talk, then you find that with all the conventional physics thrown in, you get with abundances of hydrogen, abundances of helium, and so on and so forth, and much more. And now even with what is called the cosmic microwave background radiation, where there are very, very small departures from homogeneity. So it looks like this level, it is a good approximation to actually do what I said do. Okay. And in fact, some people didn't want the Big Bang. So, Narlikar and so on, they had the steady state universe and so on. But the evidence, I'm not a cosmologist, but the evidence is overwhelmingly that we have what is called a Big Bang cosmology. And as I said, also these kind of places where you do not know how to evolve further are all over the place, and they're called the singularity theorems. All right?
Sir,
Yes.
you said that when the curvature tends to infinity,
Yeah.
the quantum gravity become prominent.
Before that, right?
Can you elaborate more on this effect?
So as I said, you see, this is the Planck length, right? This 10 to the minus 35. That is when you expect at those distance scales, quantum gravity effects are going to become important. So before it goes to infinity, it is going to go to 10 to the 70 meter to the minus 2. Right?
So what are these effects that become prominent at those length scale but not at these length scales?
Yeah, exactly. Those are exactly what you believe would be quantum gravitational effects. Place at which quantum gravity would be important. I don't know what the theory is. I don't know how to normal physics at our length scales, but the indications are that at that length scale, certainly there is something which will come into play, which you have not accounted for, and perhaps that would then allow you to complete your physical understanding where it just broke down. Okay? Let me get to the next thing, which is like, if any, oh, okay, go ahead, yeah.
Sir, you said.
Okay, I may not be able to complete my talk, but that's okay, I don't mind. So again, if it is something which is obstructing your understanding directly, then ask me, otherwise we'll take it later.
Sir, you said that the observation we do for large distances, right?
Yes.
So how is locality maintained?
Let's come, because I don't understand the question very well. Okay, so to understand the question, it would take some, discuss it later. Right now, all I want you to takeaway from here is that if you look at general relativity and you look at its equations, very often these equations, when you evolve them either to the future or to the past, result in situations where the curvature blows up and you cannot evolve any further. Okay? That happens, before that happens, you might expect that quantum gravity could save you. Because quantum mechanics has this ability to save you in other circumstances, right? The fact that you exist because of quantum mechanics, right? I mean, if you're made up of atoms, the atoms have a proton, the proton has an electron running around it, and then Maxwell's equations will tell you that it's going to radiate and fall in, will collapse. But you're not collapsing, right? So what is that stabilizing you? Quantum mechanics, right? So quantum mechanics has this amazing way of curing classical singularities. And so maybe it can do it here. We don't know. Okay, but I can at the end. Huh? Okay, so let's go to this, which is probably, to workers in the field, even more fascinating than this singularity business. Okay, and black holes, I don't mean by, I'm a mathematical generalist, not astrophysics of black holes and accretion disks and how you detect them. No, their property to the Einstein equations, right? That is what I'm talking about. So let's go ahead with this. So in general relativity, as in special relativity, as I keep saying, the speed of propagation locally is limited by that of light. That's what everywhere. It's just that these light cones can swirl around because the geometry is curved. They're not like in special relativity. Now, if the structure of all these light cones that your light is trapped somewhere in the interior, there is a notion of interior where light cannot come out of, and there is a notion of exterior where signals cannot move, then you say that you have a black hole. Okay, so why black? Because come out to you, and a hole because things can fall in but nothing can come out. So these are configurations which are called a black hole, and I'll show you, just to give you an intuition about what it looks like. I'll again go to one dimension less. So the circle next diagram are to be thought of, they're actually the surfaces, all right? And with that, so let's go over here. So if I go far away from a, then light behaves pretty much as it does in our usual space-time, okay? So there will be a set of radially outgoing light and a set of, so if you, for example, if you have a sphere, right? There's a circle, but you think there are two sets of light rays normal to the sphere, right? One is those guys who are shining your torch outside and the shining the torch inside. So what happens to the guys outside? They just diverge, right? So what happens to the guys inside? They converge. All right? So that's exactly what I've shown over there. There are these outward, which are diverging, and there are guys inward, which are converging. So nothing is particularly crazy over there. But what the gravity for a black hole does is that it takes this light cone, and instead of having it rigid everywhere, due to the curvature, tilts it like this. Go inside towards the center, the light cones are tilting. And remember, the rule is that you can only be within, light and all possible signals are within the light cone. They cannot, you can't go outside, right? So look what happens over here, right? So this is a light cone, it is tipping, 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 tipping. Here, right, if you look at this light cone, then what were the outgoing guys also fall inside, right? Because everything has to be inside the light cone, right? So everything falls, and this is the singularity. This is where things blow up. So the black hole in the center has a place of infinite curvature, right? And now you see, as you're going inside, they're tipping, 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 and finally this place over here where the outgoing guys, so here the outgoing guys all escape, right? But here the outgoing guys sort of, they neither escape nor do they fall in. Somehow linger over there. And that place is called the horizon. The trajectory of those outgoing rays is the horizon, right? And from this diagram, you can see it's a circle times the real line. So actually, it is a two-sphere times the real line. That is the topology of what is called the black hole horizon. And that is what separates the interior from the exterior. And everything inside is trapped. All right? Now, as I said, the event horizon is three-dimensional because it's sphere times the real line, and it has, of course, two-dimensional cross sections. And these two-dimensional cross sections, there is a geometry, right? Because that is our whole fabric of everything is that you can compute the area of these cross sections. And up to now, what have we been talking about? Maybe the mathematical techniques, differential geometry, metrics, causality, light, and suddenly this area has something to do with something completely different, which is how you describe steam engines and calorimeters and things like that. Thermodynamics. What the, I shouldn't curse, but what the, hell does have to do with the area of horizons? I mean, why? It's completely absurd. Why should this happen, right? There's no reason for this to happen. Okay, so let me tell you a story of what that is. So first, for those of you who are just exposed to the concept of entropy at the beginning, tell me if I can skip this, but otherwise I'll go. If no, if there is silence, I will speak. My general rule. Okay. So what is entropy? Entropy is a measure of disorder in a large system. A large system is one which is made up of a number of microscopic constituents. For example, a box of gas is made up of 10 to the 23 atoms. And the disorder refers to the disorder in the arrangement of these microscopic constituents. As you know in your daily experience, closed or isolated systems tend to evolve towards more disordered states, not less disordered ones. Microscopic constituents tend to mix up with each other, creating a more and more. For example, put sugar in your coffee and sweet, it doesn't spontaneously unstir, right? You've never seen it happen. Or all the sort of oxygen molecules in this room sequester in one corner and we all die. I mean, that's an occurrence in the history of human civilization as far as we know, right? Things are, that is a very ordered thing. All the quietly, it's a very ordered state, right? Coffee and sugar separately, it's very ordered, right? So what happens is that you get more and more disorder. This is elevated to the status of a law, which is called the second law of thermodynamics. It states that physical processes can never decrease in an isolated system. Now, entropy is a precise disorder. I can put a number to it through what is called statistical mechanics. Calculated if we know what the microscopic constituents of a system are and how they behave. So what can entropy and disorder possibly have to do with a black hole? And this was sparked out by John Wheeler, who was Feynman's advisor, and he had a bunch of students. I think he has graduated the maximum number of students from Princeton. I mean, he's no longer alive. And one of them was Bekenstein. And Wheeler asked Bekenstein what would happen if he took a cup of hot tea and he poured. So now what happens? What Wheeler meant was that supposing you have some object which has entropy, and now you chuck it into the black hole, now it's gone. So as far as the observable universe goes, you can never reach out to that object, it's gone. It will never communicate with you, right? So in your observable part of the universe, the entropy has decreased. Okay. Now, of course, one can say that, well, for people who know it's a statistical thing, it's something like that. Perhaps there's a violation because other things are lepton number is violated if you chuck leptons in black hole, right? In your observable, maybe the second law is, we don't know, or maybe there is the entropy is all there in the black hole or something. But Bekenstein did not do that, right? And this is where you see great physicists. He was only 25. His PhD thesis, so the person I worked with, Abhay Ashtekar, who's some very well-known relativist, that's an understatement. He said that Bekenstein's thesis is one of the best PhD theses he has ever read. Right? Bekenstein was only 25 and actually he had to withstand a lot of criticism. He said, no. There is something which I can measure from the black hole, which when I combine with the entropy outside it will restore for me a simple law. So that was his whole prejudice and his intuition. And what he found was that when the black hole, the mass of the black hole increases, and the Einstein tell you that if the mass of the black hole increases, the area of the horizon of the black hole also increases. So each time you change something, the area of the horizon is going to increase. So Bekenstein has some papers where he keeps on chucking black hole, right? And his main aim is to, have the biggest decrease of entropy outside, smallest increase in mass inside. And he found through these thought experiments, which haven't gone through all of them in detail, but the conclusion is that if he took something which was proportional to the area of the black hole, plus whatever was the observable entropy outside, combination would always increase. So this is called the generalized second law. And he could even what that constant was. It was approximately our old friend area, that 10 to the minus 35 meter whole square. The area divided by the Planck area multiplied by a factor of Boltzmann constant was the entropy which he would assign, and it's an enormous entropy, huge, right? The entropy of the sun is smaller than, much smaller than a black hole which would have been formed with the mass of the sun. Okay, so there's a gigantic entropy which he has assigned over there, but then is, because there is the Planck area over there, one may ask, okay, the black hole has an entropy, but what are the microscopic constituents which give it this entropy? And then you see the Planck area over there. Planck area has something to do with quantum gravity, and so you ask whether maybe the fact that a black hole got entropy which is proportional to the area divided by the Planck area, maybe they explain quantum gravity. And indeed, different theories of quantum gravity assign different explanations for what is called now the Bekenstein-Hawking entropy. And there is a longer story, but I probably have already almost run out. I have run out of time, basically. So GR is incomplete due to singularities. Quantum mechanics often resolve singular behavior. Motivation is to find quantum gravity to resolve the singular behavior of classical GR. And there is this mysterious connection between GR and thermodynamics, which suggests that black holes have entropy. Quantum gravity provide an understanding of the origin of entropy. Okay. Since I started a few minutes late, I can take a few minutes and I can just stop whenever you want me to stop. Okay, so whenever you tell me, I'll just stop, because I think the basic thing which I wanted to communicate to you, I have done, and the rest of it is what are the approaches, etc., etc. Now, let me return to the question of observations, and this is still, people are just struggling, they want some observational contact with quantum gravity. It's not yet conclusive, it's not yet there, but people are really trying. Now, there are two sets of, there are more. I mean, there's another thing which is coming up which I don't have time to tell you about, but there are two sets of relevant observations. One is perhaps, because in quantum gravity, at the smallest distance scale, the notion of space and time itself, you replace it with some discrete structure, and then you start worrying about Lorentz invariance, which is a and sometimes there might be a breakdown of Lorentz invariance, and that is very tightly constrained by experiments. So nature is telling us that things are basically at a very small level. They are what is called locally Lorentz invariant, but I won't get. I'll tell you about the other thing a little bit, which is a laboratory which is already there, which is our universe and in cosmology. So as I said, our universe, to all intents and purposes from data, started at the Big Bang, where the vicinity of that expects quantum gravity effects. So could signs of that be, there's a billion years, could signs of that be measured today? And of course, this whacked out idea, because, I mean, so much time has passed, right? I mean, how are you going to be able to see anything at all? But it turns out that the theories are also wacky enough that it might just be possible that you could see something. So what is this? The universe at large scales, as I said, looks very uniform. Unless the universe was born in a very uniform state, it would be very hard to see how this can happen. Why? Because if it was a uniform state, then different parts of the universe would have to interact and kind of homogenize. Larger is the region of homogeneity, more time would be needed for these different parts to interact. But remember, the Big Bang is a finite time ago. And it turns out when you put in the numbers, for the large patch of homogeneity we can see, whatever we can see is limited by the speed of light, right? So whatever we can see, and by other things which I won't get into, but what we see, that huge patch of homogeneity, there is not in for the universe after the once space and time started at the Big Bang for things to homogenize that much. So therefore theorists invented a phenomenon which is kind of, I don't know if they're cosmologists here, but like it's kind of bonkers, but it's called inflation. And what it really tells you that very, very shortly after the Big Bang, there was a rapid phase of expansion. And so the small already homogenized patches at that epoch are now blown up to the large patches we see today. Okay, so that is roughly what inflation is about. And then it turns out, because of this peculiar evolution due to inflation, very smallest scales a long time ago, if you had not too much inflation, might just about be visible as the largest scales today, by which we mean the cosmic microwave background radiation. So we can talk about this more later, but people are really trying theory of quantum gravity, at least in my community, fits things over there. Again, as I said, I probably could wind up in another 5 to 7 minutes. So, but please veto or do whatever. I'm happy to stop at any time. Sorry? Okay, good. Okay, so approach quantum gravity, historically, those derived from particle physics way of thinking. So the most prominent approach is string theory, and then derived from people who are from the general relativity, and those put space-time to the space-time geometry to the, and those are loop quantum gravity, Regge calculus, causal sets, causal dynamics. These are the various things. Middle are these Euclidean gravity of Hawking and asymptotic safety, which is another interesting one. Looks for a non-trivial fixed point, not a Gaussian one, but a non-trivial one. This was Weinberg's idea. I work within the approach of LQG, and in this approach is fairly conservative. One does not all interactions like in string theory, but one comes out with one's contention that there is some robustness associated with quantum fluctuations of geometry. Maybe that, if we can get a handle on that, that will already tell us quite a significant amount of physics. So we are mainly concentrated only on the geometry part, not on the matter part. Loop quantum gravity, and very quickly, if you look at quantum mechanics, for those of you who have gone through quantum mechanics, you have a particle with position q, momentum p, q and p turned into quantum operators. They are wave functions and there are quantum fluctuations due to the anti-principle. So you have this as your background, that is your what is called the kinematics, and then the wave function evolves in time. That is the dynamics, right? So that is the Schrodinger equation. Now Q, which is the configuration, is like the geometry at an instant. It's a geometry of space, right? Because it's space-time, so the geometry of space at an instant of time. P is like the rate of change of that geometry, like the velocity. Since spatial geometry is everywhere, right? So this becomes what is called a field theory, and one has infinitely number of Q and P, and that of course makes it a field theory, which is complicated. What LQG does is it finds a nice way to turn certain functions of these Q's and P's into operators which are subject to quantum uncertainties and which act on wave functions. So that part is under control. What is not under control is a satisfactory construction of the extremely complicated function appropriate to gravity. So that we don't know, and that is something which I've been working on throughout my career. But one can already apply, one doesn't have the full theory there, but what one can do is try and do what one can do, which is one can take LQG ideas which one has developed over the course of years and apply them to physical situations in which you believe only a few modes of the gravitational field are important. For example, in the early universe, you think homogeneous and isotropic, and so you could try and focus on the loop quantum gravitational physics of only these homogeneous gravitational fields where you switch off all the other modes. Or if you're looking at spherical collapse to a black hole, physics of spherically symmetric fields and not worry about the non-symmetric modes. So if you to these physical situations, then you actually, they give you a hint of this exact possibility which we talked about, which is of resolving the classical singularity. Due to strong LQG effects near the classically singular region, there is rather active gravity, there is a strong repulsive force which is of purely quantum gravitational origin, hence the collapse to a singularity. So instead of collapse to a singularity, you go after a critical density, you bounce. So you have what is called a big bounce instead of a big bang. And people try and say, well, if you replace the big bang with the big bounce, is there any signature in the CMBR? And that is a lot of activity in this field called loop quantum cosmology. Okay, good. So while such applications of LQG ideas open up fascinating possibilities, they also in turn provide input to its foundations, which I work on. I work on basically its foundations. I do a little bit of quantum cosmology as well. And then in turn, the hope is that folding in these inputs into the foundation place the hinted results on a firmer footing. That is how physics grows, especially when you don't have too much experiment. This is what we do. Okay, so let me conclude. Quantum gravity is a fascinating subject. I hope to convince you with deep conceptual implications. It is the quantum mechanics of space-time itself as opposed to quantum mechanics in space-time. While direct experiments at the Planck scale are impossible, in recent times we might be just being beginning of the beginning of the beginning of experimental quantum gravity, tests of local Lorentz invariants, and the hope that precision cosmology would tell us something about the early universe. So with that, I thank you a lot for your attention.
Small gift for you.